We had a ton of fun with this one. We started out with that velocity test, water blasting up into the air, hitting the ceiling, adding in some of that smart technology features, which just takes it to a new level. So in my opinion, there is one clear winner. It's gonna be the Hey, what's up everybody? I'm the Pond Professor here, and I am excited about today's vlog because we are gonna announce the winner to our pond pump contest. So remember, Home Depot DIY pump, and then we went through those $1,000 pro pumps.
We want to pump you up.
Which creates stuff like this. Stay tuned, you don't want to miss this one. So our next part of the test is actually to measure the output. Attaching a 2-inch pipe to the discharge of these pumps, fill up a graduated cylinder. So this is marked off at 5, 10, 15, 20, 25 gallon marks. What I'm gonna then do is I'm gonna time how long it takes to fill up to that 25 gallon period, and then we could do some calculations to figure out the gallons per second, gallons per hour, as well as gallons per minute. 25 gallons, 14.79 seconds. So that went so fast, I would rather have a little bit more volume of water. So we're gonna take it all the way up to 50 gallons. It's gonna double the number, so it's gonna be a little bit more accurate. So the first one, 14.79. So this one should be coming in at around 30 seconds if everything adds up properly. And that's what we wanna double check. 31.58 seconds to fill up to 50 gallons. Now it was a little bit slower than that 25 gallon mark. The only thing that I could say about it is we're pumping water higher. So that's gonna make a slight difference on the head pressure for the pump. So what I wanna do now is we're gonna change this pump out. We're gonna switch it over to the SLD pump to see how it actually measures up against this. And then what we're gonna do is we're gonna go up into my office. I'm gonna do some actual calculations so we could start to understand all these different dynamic forces that are occurring inside of the piping system as well as the pump, which is actually responsible for the water output that we're actually seeing. So a lot of cool stuff happening here. The bigger the project it is, the bigger the pumps, the more important this actually becomes. So I'm always super conscious about dialing in the right volume of water from an aesthetic standpoint as well as a functional. So our next step of the experiment is to add a third pump to the mix. This is what we call our AquaSurge pump. As you can see, it has this cage going around it. It does not have a solids handling capability. What it does pick up on is it's a fraction of the electrical cost. So what I want to do now is I want to do the same tests, and we want to see what type of output we're actually going to have. From that, we can do a simple calculation. We can compare all the different pumps. All right, so we got some good data here. So I've had a blast out there doing all that stuff, playing around with the different pumps. Now I want to actually get down into the results of what happened. So if you remember what we did, we had that big tank, 50 gallons. We put the pumps in, we had a 2-inch pipe going up and over, and we measured the amount of time that it took to fill 50 gallons of water. Here are my results over here. I have for the DIY pump, we filled 50 gallons of water in 31.58 seconds. This equates to almost 5,700 gallons per hour of flow rate. We also did the AquaSurge 5000. That one took a little bit longer, 39 seconds to fill the same 50 gallons. That equates to 4,600 gallons per hour. The SLD, that one flew. I mean, we're talking only 23.66 seconds to fill 50 gallons of water, 7,600 GPH. But what I think is interesting about this is I love having that additional water, but there's a cost associated with it. Cost of the pump is actually more, but also the electrical cost is more. So what I want to do now to find the true winner is to understand all these different numbers. I want to understand which one gets clogged up, which one doesn't get clogged up, which one is most energy efficient, what the actual construction of these is like, which is what we're going to talk to Dave about in just a few minutes. But I wanted to go through all this stuff first to see exactly what we're looking for. So a few things that I really want to stress here. When you're choosing a pump, you have to understand the parameters. You can't just come in and say, I need 5,000 gallons per hour. Where's that coming from? There's also head loss. We have to figure out the total dynamic head. So let's go to a website over here, and this will tell us exactly what that looks like. The total dynamic head is a combination of several factors. How high you're pumping the water, how far you're pumping the water, as well as the size of the piping. I have a couple of cross sections of pipe right here. This is the pipe we actually used, 2-inch over here, 1-inch on this side. You could see the physical difference between those two. Huge difference. The amount of water that can go through this is going to be considerably more than this, and we illustrated that with our pump tests because remember, we had that water shooting way up high when we choked it down because all that water is trying to jam itself through a small pipe opening. When that happens, it puts back pressure on the pump. So flow rate we're looking for at 80 GPM. So that equates to 4,800 gallons per hour. The reason I'm looking for 4,800 GPM because I know how wide my waterfall is. I'm looking for a waterfall about 2.5 feet wide. I have very simple calculations to determine how wide a waterfall is with the proper flow rate. For every foot of waterfall width, we need 1,500 to 2,000 gallons per hour. So when I start multiplying that out, when I get to about 30 inches, I need about 4,800 gallons or so, 5,000 gallons per hour. That equates to 80 GPM. I mentioned this before. We want to make sure that we go with the proper pipe size, 2-inch pipe diameter, and let's just say 50 feet of piping. So it is 50 feet from the pump all the way to the top of our waterfall. And I also have a difference in elevation from the top of my pond level all the way to the top discharge point. I'm just gonna say it's 5 feet. This is just an average backyard. We don't need pressure. Remember, I talked about this before. We're really not looking for high pressure or water velocity. We're looking for volume of water. Now, once I add all these different numbers together, I come down here and I click total dynamic head and boom, 10.6 feet. That is a critical number. A lot of times, unfortunately, I see people saying, I'm pumping the water 5 feet high, I have 5 feet ahead. It's not the case. It's actually double that because it's a combination of these different factors. So you have to understand your application. Once I know this, now I could actually come in and I could actually plug it into my different pump curves. Let's start up here on top. This is our DIY pump. 4,800 gallons per hour, 80 GPM, 10 feet ahead if you can read that. Perfect. 80 gallons a minute. Nailed it.
You smart.
That pump is going to work perfect for us in this application. Now I have the SLD 5,000 to 9,000, 10 feet ahead, right through this section here. That's the SLD 5 to 9. I'm getting 7,700 gallons per hour. Getting way more water than we need for this application in waterfall. In some situations, you may want more water, but you have to have the tools to create the educated decision. Is it worth the additional power consumption? Or possibly you could use some other technology, increase or decrease the flows and things like that. It's a contender, but I think it's a little overkill. Now the AquaSurge 5,000, look at this. This is perfect. So here's that 5,000, 10 feet ahead. We are at 4,750 gallons per hour. Slightly less than the DIY pump, but if you remember from that kilowatt calculations we did, this one is gonna save us $900 a year in electrical costs. That's actually gonna pay for the cost of the pump many times over because that pump comes with a 3-year warranty. So putting all these different things together, we wanna find the right pump for our application. There's always gonna be some unique situations, but I wanna give you the tools to be educated so when you go out to purchase your next pump, you could actually start to figure all these different pieces and parts out, which is gonna help you make that better decision. I want to go through some of the other differences between the two different pumps. You can definitely see two different styles here. One of them is going to be sitting down in a flat position with an orientation, and the opening to the volute is on the end. Now this one has a screen down on the bottom, but it's sitting flat. So this is gonna pump the water down a little bit lower. And in certain applications, that is really, really valuable. For what we're doing, either one of these will actually work. The other thing that we have a plastic body construction with this one, which actually makes the pump somewhat lighter. So we still have all the guts and all the internal components, which is responsible for the pumping itself, but then it has a plastic shell around it. This one is a cast iron, a lot heavier. And again, in certain applications, that is great. But if you ever have to pull this pump out, if you're down inside doing maintenance on a pond or something like that, this style gets a little bit difficult to work with. There's this little actuating arm here. So this floats. If this is in water, this is gonna float up, and you can see it's gonna push this arm into an up position. This is going to allow the pump to operate. So if it's plugged in, the pump will be operating if it's full of water. If the water level drops down below this point, this is going to drop a little bit, and then that arm is going to click into the off position. This is a sump pump. This has a very specific application. It's designed to turn off and on according to rainwater, according to storm situations and things like that. This pump is designed to operate 365 days a year. Both of them have actually 3-year warranties, but when you look at the hours, completely different. They're both approximately the same wattage. I think so far we have some pretty good data to work with for a successful water feature project. All right, Dave Kelly's all ready for us. Why don't we go check in with him, because he can give us all that detailed information that we're looking for about these particular pumps. Hey, what's up?
What's up? What's up?
Well, thanks for getting everything together here for us. So you guys met Dave Kelly already. Product guru, knows everything about all of our pumps, filter systems, and all that. Could you give us some information on the difference between the direct drive pump, which we actually still use on a lot of applications, but this is kind of that DIY pump. We picked up one at Home Depot, very similar to this model.
You guys been doing all the testing in the back on.
Exactly.
From a design perspective, because we used to run into it years ago when we used to use some of those similar style pumps, is the way they're designed from the internals. So what you don't see on the outside, you know, if you know how it works on the inside, that's where the problem occurs. Basically, the interior of this pump right here is all your electronic components, and everything that's happening is water's wanting to come into here, whether it's the mechanical seals, the O-rings, the gaskets, everything where all the hardware is actually put together. So it's all leak points for water to get into. That's a concern, because what they have in here is actually oil filled in all those type of pumps, and not just a little bit of oil. We're talking anywhere from a third to half a gallon of oil. So you remember you talked about decades of working together. You know, back in the day when there weren't really a lot of water feature pumps, we were using other stuff out there in the industry. Some of those pumps didn't happen all the time, but boy, we had it happen where they would breach. And you got a water feature, and you have that oil come out there, and you get a third to half a gallon of oil, an oil slick on the top, an oil slick on the rock.
This one's a little different because you don't have quite as much oil.
No, and we designed some other pumps out there to avoid that, to basically get rid of all that oil. And really in this pump in particular, the only oil is down in this little area. It's a mineral oil we use. It's a small little chamber where the seals are at. So this whole area is dry. It's void of any oil, just air basically filled. And then to take that one step further, latest design of pumps is this style right here, which is that asynchronous can pump. Because when you pull this out, it almost looks like a beer can or a Coke can with the top cut off of it. On the inside of this pump, it's air or it's oil. On the inside of this pump, they fill it with a hot liquid epoxy. And that goes in all the nooks and crannies and void spaces in here, and then that epoxy hardens. One big piece that's all hardened all around the electronics.
No way for water to get into.
What's great about that is there's no oil in it for it to spill out. But even more important is all these seals I was talking about, water's always trying to get in. If water does get in anywhere around here, it's just going to be met with a huge giant solid piece of epoxy. The nice thing about this type of rotor assembly too is if you ever have an issue, one of the things you can do, and like 80-90% of the time it'll fix the problem, is you just basically change this out. You pull this out, inspect it. If something's damaged with it, you need a new one, you drop that back in, put everything back together, and you're good as gold.
Now, from an efficiency standpoint, these ones much more energy efficient. We use your kilowatt tester, which worked out awesome to tell us the exact wattage, amperage, everything that we're pulling. Now, with all these mechanical seals and all that stuff, that's friction points, right? I mean, so you need a lot more horsepower to do that, and it's consuming a lot more. It's also a different style. I mean, it is more for solids handling, but each one of these seals, the tolerances on those things is
it's crazy.
Microns.
It's microns. Yeah, it's like glass. You can't touch them with your fingers. It is very, very temperamental, both in the actual manufacturing of it as well as the assembly at the factory on it. So there's more stuff that can go wrong in this with all the pieces and parts and stuff that are put together. If I take this pump and I pull it apart and show all the components with it, and then I take this pump and pull it apart, there's like 4 components versus about 50 components. Yeah, just because this is all sealed up.
This is just a killer.
It's been a great pump.
Some of the other stuff that you developed, tell us about the Smart App.
Our Smart App, our pump controller right here. So this actually plugs in. And what that does is the pump plugs into this, and this allows you, if it's a type of pump that you can actually run on a variable speed, like for the AquaSurge, a 2,000 to 4,000 and the 4,000 to 8,000 pump. So they come with a little controller like this. So on the dashboard of the controller, you can raise or lower it and basically get an energy savings when you do that. But not only that, it's got a Wi-Fi chip in it, so you can connect it. So I have my app here that has my dosing system, my lights, a thermometer. Right now my water temperature is 50 degrees at home, you can see that. And then there's my pump. I can actually take the pump speed. It's running at 7 out of 10. I have an AquaSurge 2,000 to 4,000 on it, and that is a good flow for me. It seems like a nice flow, but I can dial that down right here. I can turn it on, turn it off, and now if someone's home watching, they're going, what the heck is going on? Because it's changing. This will tell you exactly how much it's running. I got 127 volts coming out of the outlet there. My pump is running at 1.87 amps and 191 watts. And as I raise and lower that flow, I'll see a savings, or I'll see it start to use more. And then you can get real geeky with this, because you can go into automations, and like I have mine set to run like at 9 or 10 at 4 at night. to like, you know, midnight or so
Yeah.
when I want a higher flow. When I'm not out there using it, I can save some energy. I have it then drop down automatically to run at a 7, 6, or a 5, whatever you want to run it at. And you're going to save that energy consumption when you're not out there. It's enough to support the life of the system and keep everything looking clean and clear, but you got your party mode when you're home, and you got your more relaxed energy conservation mode later on.
Exactly. Well, in today's world, I mean, price of power keeps going up.
Oh,
Everybody's concerned about their carbon footprint and all that stuff. But when we have life inside that pond, we want to make sure that we're still delivering the proper flow, dissolved oxygen.
Yep.
But there's another feature on there. So if you have a problem, or if there's a problem with the pump and it shuts off, it'll give you an alert.
I talked about the automations. I have mine set up that if the pump goes off, it'll alert me. So if someone goes over and unplugs it, or there's a problem with it, the pump fails for whatever reason, or the electrical outage, you know, at my house, it'll all of a sudden notify me no matter where I'm at, anywhere in the world, it'll tell me, hey, your pump is not running, check it out.
And actually, in our comparison, we talked about a $1,000 Pro pump compared to a $200 DIY pump. That $1,000 actually included that smart controller.
Right. Yeah,
it
because
was
you
the
use
smart
the SLD.
controller plus that, so
Correct.
you have that safety, you have all that stuff. So that's awesome.
Yeah.
All right, man. Well, I appreciate your help.
Sweet.
Let us go figure out a winner. So we had a ton of fun with this one. We started out with that velocity test, water blasting up into the air, hitting the ceiling of our roof over a 2-story building. Awesome stuff. We also did a flow test, measuring how fast the water's going to fill up a tank, and we cannot forget the debris test. So all the muck, the mud, the junk that we threw in to try to destroy these pumps. And then we looked at the kilowatt hours. We wanted to know how much power these things are going to consume, as well as the amount of water that they're going to produce. Finally, we wrapped everything up. We went over all that stuff with Dave. We wanted to learn about the construction methods. We also wanted to see if we could make these things smart, adding in some of that smart technology where we could actually manipulate some of the features, which just takes it to a new level. So in my opinion, there is one clear winner. It's going to be the AquaSurge 5000. So definitely check out part 1 so you can learn all about these different tests. But please let me know your thoughts. I want to know what you're thinking about this pump that I chose. And then also let me know if you have any projects coming up, because I would love to be able to help you on any one of your projects. Stay tuned for more incredible stuff that we have coming up right here with Pond Professor.